Hi, everyone. Welcome to Foresight's Existential Hope Podcast. We're delighted to have Adam Marblestone here today. I think, Adam, I was trying to think back of how I first came across your work or you. And I think it's because you wrote a workshop report on a positional chemistry workshop that was really going into a lot of depth in terms of what has happened in nanotechnology recently, but not only recently, but also in the past, and what we can do to possibly speed that up. And I was very excited about that, given Foresight's obvious history in nanotechnology, and reached out to you. I think pretty much that was maybe the first time we were in touch. But since then, obviously, you've been very much revolutionizing the field of meta science through your work on focused research organizations, and on really trying to elevate a lot of projects, not only in biotech, but also in neurotech and lots of other fields. So I think it's just really interesting to see how you've really managed to have pretty large effect on a field that is really quite that we've struggled to make progress in. So thanks a lot for that. I'm really happy to have you here now.
Thank you.
Maybe you could just start by giving a little bit of an intro to you, because I think it's interesting that you started out in really very much in the nitty gritty of a scientific discipline and then took it all meta eventually. So please, how you got to where you are.
Thanks a lot for that. And yeah, it's hopefully just the beginning. Yeah, so I'm co-founder and CEO of a nonprofit called Convergent Research. And we think of ourselves as a science studio. So we're best known for creating this category of projects called focused research organizations that probably we'll talk about. But we're interested in enabling researchers to work on problems where essentially you're building a piece of infrastructure for the scientific process itself. There are many different types of problems that the FROs can apply to, but a major category is sort of scientific infrastructure. Think about the Hubble Space Telescope. That is not really a product in the traditional sense, but it is a system that had to be engineered. It's also not a scientific discovery. It's not somebody's thesis, right? It's a piece of infrastructure that's used by research itself. So we think these focused research organizations are particularly useful for filling bottlenecks that exist in the system on creating scientific infrastructure. And yeah, I got to this through a bunch of much more object level questions, but where myself and some colleagues realized that this was a gap that had some common features across many of the different object level problems that I've been interested in working on. So when I was a teenager, I was reading books like Eric Drexler's book about nanotechnology and many other science and science fiction books. And I had really broad interests across science, but I was particularly interested in this sort of very technologically enabled view, maybe that is closely related to nanotechnology. I started out, I had lots of intellectual questions I was interested in, like how does the brain work or something like that. But what was being described technologically would be okay, you could have really powerful physical access to the brain, or how would AI work? You could make really powerful computers. And so somehow this nexus that nanotechnology did represent of sort of biochemistry, engineering, physics, chemistry was what I got really interested in. And as I progressed in that field, both working in nanotechnology and in synthetic biology and neuroscience fields, we just kept seeing this problem that there were these sort of early stage parts of research where you need to build something. Might be a new type of microscope or something, or it might be a new machine for fabricating nanostructures, whatever it might be. And you would need more of a sort of industry-like team, right? It doesn't make sense for an individual person to apprentice themselves in all of the different skills that you would need to put together this piece of infrastructure. It made sense to divide the labor and professionalize the labor in a different way. And that's what led us to the focused research organizations, maybe most directly through brain mapping and connectomics is what led us to it. But in retrospect, a lot of the other problems in biomolecular engineering and stuff also some of them have that character also.
Okay, wonderful. Maybe we can dig a little bit into what these focused research organizations are. I know that, for example, on the Convergent website, you guys do have a pretty good diagram, but maybe you could elucidate a little bit. What are they? Why are they interesting? And especially, I think, how do they differ from traditional organizations that we've known? Why do we need this kind of new organization now?
Yeah, so I think of them as a critical mass of the right people multiplied by a critical mass of time and support to build a very well-defined thing that the market would not support you building as a traditional for-profit startup, right? So in some ways you can think of they're sort of like nonprofit deep tech startups. I actually think there's a lot of room for experimentation on all sorts of aspects of this. How is this set up legally? How is this set up structurally, financially? Convergent Research has particular ways that we started doing this. We have a parent nonprofit, and each of the individual FROs is a subsidiary LLC entity that kind of packages people and resources and could then be repackaged after the FRO in different ways, depending on what happens. But they live during the FRO itself within the parent nonprofit, which also provides a kind of back office support structure as well. But there are these concerted pushes, and you can think of them as borrowing certain key features that startups have. So I think some of the features startups have, they tend to be very laser focused, very strong unity of purpose of an entire team. It's not really each individual researcher pursuing their own individual question. That's actually part of why we call it convergent research, is I think of most academic research as divergent, deliberately divergent. So my thesis has to be different than your thesis, both to get academic credit for that and because that's what you're trying to do. You're trying to come up with a new idea. Convergent research is like, how do you get 20 or 30 people to all build the same microscope or something for 5 years? It doesn't mean that there isn't major scientific risks and questions that the team figures out how to pursue, or that it doesn't pivot. It doesn't have to be a kind of straight build out of something. It's still research, but it's startup inspired by that unity of purpose. There's typically a small founding team that then handpicks the rest of the hires, not only for their sort of technical skills or background, but also for their alignment with that mission. So you build the team in a way that's very similar to the way a startup builds a team. And then the projects tend to involve a kind of amount of operational coordination or tight-knit coordination. That means that they also operate in a way that's pretty similar to how a deep tech startup works on its sort of internal technical development. But then these are often creating some kind of public good. So it might be an open source data set. It might be a tool that other researchers will use. In some cases, they're also capturing IP. In some cases, those things will also spin off into companies, but there's often a major open source public goods component.
Well, and I guess since I just remember, I think the first time when you guys discussed FROs or FROs, at least in the Foresight setting, was like a few years ago on a seminar where you guys dug into the concept. And at that point, it was still very much in the conceptualization stage or in the birthing stage. And now here we are like a few years later, and there are a bunch of FROs out there. Looking back from the first time when you discussed it, at least in a Foresight setting, what have you learned in these few years, but also which FROs have come on the horizon? Is there another sector ripe for an FRO that you want to point out that other folks listening to this might be able to take on?
A couple of the things that we've learned that I'm excited about. I think the biggest objection that we got, maybe circa 2020 kind of era of thinking about this before we had actually launched them. They're still early, right? We still haven't gone through a full 5-year cycle or beyond 5-year cycle. It's all been happening pretty quickly, but the oldest one is about 3 years old, slightly less than 3 years old. But one of the biggest objections that we got or questions that we got was, can you recruit really great people into these FROs? Why would you do this if you can't have an academic tenure track as your main goal here? Or why, you're not offering equity in a high growth startup, or you're not offering the stability of a major industrial entity? So why would anybody join these nonprofit startups? I think we've been really pleasantly surprised that we've basically been able in each of the cases to build really strong teams. Leaders in their respective fields at different career stages have either been founders, management in FROs, or have been just joined FROs as technical contributors. And so we're really psyched about that. We've also experimented a lot with the sort of phenotype or career stage of the leaders. And you have everything from very senior people, where this is one of the last things that they'll be doing probably before they retire, to people that are very recently out of grad school. So we've been exploring a whole spectrum and everything in between, different combinations of CSOs and CEOs and COOs, different types of founding teams. I've also been pretty psyched that we knew from very direct experience, like myself and Sam Rodriguez, who is the other kind of author of the FRO concept, we both had been trying to work on connectomics and neuroscience problems. And so we knew that this was really needed in neuroscience. Neuroscience has this property. The brain is just such this huge and complicated object, basically, that the skills of people who study the brain, whose job is to ask a question about the brain, there's many other skills that you need to bring into the neuroscience endeavor that are not neuroscience per se. So maybe if you want to understand the brain, you study theoretical neuroscience or you study behavior of mice or something like that. You basically study things that are more within the neuroscience toolkit, but maybe you also need chip designers, or you also need people that build lenses or huge data systems or so on. This is something that's pretty well recognized in neuroscience. We didn't know in some other fields how true this would be. So one of the ones I'm excited about is actually the Lean FRO. So this is a interactive theorem proving software for math. So it's software that's used by mathematicians. Basically, instead of writing down their mathematical proof on a piece of paper, they write it in this programming language, which is Lean. And then what Lean can also do, in addition to suggesting next steps and so on, and resolving parts of the proof, is it can actually just say, do your conclusions actually follow from your assumptions? Yes, you are right. Your proof is correct of the thing that you claim to be proving. So this is a software infrastructure for math. And then that software infrastructure is then also going to have a huge impact on AI, particularly AI in math. And I actually think that there's a chance that AI can, in a certain sense, just end up solving math, because similar to how in other sort of reinforcement learning settings, Atari or Go or chess, the computer can just say, okay, you won the game. Good job. Here's your reinforcement learning feedback. You can close the loop without having to have a human involved in judging. Did GPT produce a nice passage of text? This can just close the loop and say, yes, you got the proof right. And that can be done automatically because you have, if the proofs are written in Lean. And so now this is being used in AI as a kind of the equivalent of Atari or equivalent of a Go engine, except for mathematical proofs. But anyway, so software infrastructure for math. And it turned out that the mathematicians didn't really have any way of organizing the software engineering project either. And it was a similar issue as in neuroscience, where maybe the neuroscience is doing neuroscience, but they really need chip designers. Mathematicians are doing theorem proving, but they really need software engineering. And so that turned out to be true in math as well. So math was not a field that we initially expected that there would be a focused research organization. So increasingly, my hunch is that there's probably a few, we think of them as FRO-shaped bottlenecks or FRO-shaped gaps per field. Or let's say fundamental field of research, maybe there are like 20, 25 fundamental fields of research. In neuroscience, I wouldn't distinguish between autism and bipolar research. I would just say neuroscience. How does the brain work? But maybe there's 20, 25 things like that. And maybe there's on the order of a handful of FROs per each of those. So that's about 100, on the order of 100 FROs that are needed, which is large, but not infinitely large, actually.
So what do we get if we solve math?
What do we get if we solve math? Yeah, it's a good question. And there's obviously different definitions of exactly what that would mean. So the most minimal version is you just have an AI assistant helping the mathematicians, and that would have implications in other fields, physics, and so on. There's another level where you really can just say, here are my axioms. I want you to prove P does not equal NP or whatever, some really hard thing, and it can just do that. There's another level where it can creatively suggest what is the theorem that you should be proving in the first place. I think not to overhype it, but I think what Lean is so far contributing to is the first of those two. It hasn't really led to the AI saying, here's the next creative direction in math. It's just said, make it more efficient to initially verify the proofs of something or crystallize the proofs of something, and ultimately to generate its own proofs for things that we already know we want to conjecture. What do you get? I think one of the really interesting connections there also is, and this is also unexpected, I think, in terms of the ways that these basic science, if you will, problems end up ramifying through different fields, but is the AI safety applications and secure sort of verifiable software applications. Can you create formal specifications of what an AI is or isn't allowed to do in some sort of very complex model? So this is David's program within ARIA, for example, and Steve Omohundro has also written about some related ideas. But can you have a sort of guaranteed safe AI paradigm? And at least some versions of that would rely on having incredibly complex software model of the system in which the AI is potentially going to act or intervene. And then can you actually prove that whatever, let's say, actions or interventions it's suggesting cannot have certain consequences? So can you actually prove something about an incredibly complicated software model? I don't know if you can do that, but I think it's an interesting research area. And then the more general question there is just, can you prove things about the properties of really complicated software systems, verifiable software? Yeah.
That's interesting. The first part of your answer reminded me also of Sam Rodriguez's work at Future House, which like just came out with this really wonderful AI tool that at least helps with bio research or other scientific research, can also, I think, already predict or propose a few experiments. Brain GPT, I think, from Bradley Love, similarly so. It can also like digest neuroscience literature and can propose a few experiments. Sometimes I think already better predicting the outcomes of these experiments than researchers in the field could, even though I guess that's somewhat experiment dependent. That would be the first chunk of this. But then you're actually saying this is the second part of actually like solving these math puzzles could lead more to provably safe AI safety implications. And I guess it's interesting how that would tie into ARIAS and David's open agency architecture work. Have you talked to, for example, Evan at Atlas Computing at all about this? Because I think he's trying to do a secure software challenge now. Would this be applicable for this?
I think they're not exactly the same challenge, but they are at least very closely related. And so if we can have research progress on proving very complicated mathematical theorems and speeding up the generation of the proofs and speeding up the verification of the proofs, that's a test bed for what are the AI systems that actually could generate software relative to a provable specification and also create that proof that it actually satisfies that specification. And so that has potentially really big cybersecurity implications, really big AI safety implications if you can really prove properties of software as opposed to just test them against individual cases, no matter how many cases you might want to test. There'll always be ones that you hadn't anticipated. And so if you can actually prove it, that's a big deal. And essentially that is the same field as this infrastructure of, can AI generate the proofs? Can AI verify the proofs? Can it generate the code that satisfies that proof?
I mean, for like computer security, I think I totally buy it, or maybe even like short term. I think for AI safety in general, isn't it like really quite complicated to formalize everything in a way that you can actually form proofs about, especially in a dynamic world that's like constantly changing? Are there like a few other steps involved that I'm not thinking about? Or
and I don't have a complete answer to that question. So that's why when you ask what you get, this is, I think, coming back to the question of scientific infrastructure, right? It would be one thing to say we have to be absolutely sold that this is definitely the approach to all real world AI safety. And that's the only reason why we're doing it. But we also get helping mathematicians along the way. And so if you can find these bottleneck points, it turns out that writing down proofs on paper and not having a way of actually verifying them turned out to be a bottleneck that affects these different fields. But I think there's many different versions. And some of the versions on the AI safety application, as I'm understanding it, they wouldn't necessarily rely as much on actual formal verification or proof. They might rely on a model that is trying to infer how likely it is that various outcomes can occur, but that model being separate from the agent model that's actually proposing the actions, and having these separations where you have the AI scientist that can estimate how likely it is that you violate certain conditions. But it all depends. Can the AI come up with the specifications itself, right, of what the safety spec is? Can it come up with what is it that you need to prove? How do you prove that? So there's a lot there, but it all depends on AI accelerating in some significant way for it to be meaningful.
And I guess, can I do that in a way that we can prove is safe itself? Okay, but no, you don't have to solve all of AI.
Anyway, so it turns out that's a FRO that is in math, that we are trying to select these as examples of something where there's a missing piece of scientific infrastructure, but also where there's this long tail possibility that if you make that infrastructure, it could have much larger implications. It's great if it helps some math grad students verify their proofs and write their papers faster. It's really great if it is a part of AI safety that wasn't otherwise accessible. And we're building the infrastructure, you end up somewhere on that spectrum of outcomes.
Just if it can help a little bit with computer security, that would be amazing. That would be a very different world and very much worthwhile doing. And math probably very much.
And interesting that even though it is so important, these are not infrastructures that are necessarily being built by the private sector or by the sort of government-backed science establishment.
Really much. Unfortunately, very much not. Is there any other field, like, for example, for someone listening to the podcast afterwards, are there any areas that you want to direct them to, or any specific requests for RFO proposals, or are you mostly guided by what is being proposed to you, or how does that process work?
That's a great question. It's a very multi-sided thing. So we interact with people that we think have a sense of what some of these bottlenecks are across different fields. We also just have an open ability for people to propose to us. We also interact with funders to try to align on what the interests are. And we sometimes do things like host fellows or host workshops, or try to, in a more directed way, generate the thinking But something that's interesting about this is that there are things at many different stages. So there's some cases where someone already basically has the roadmap for the FRO or something close to it. We have one on single cell proteomics that was launched at the beginning of 2023. In 2018, that group basically wrote a paper called Transformative Opportunities for Single Cell Proteomics, where they basically just laid out the different things you would have to do. And just they didn't have the organization or the funding to do it, but the idea was there. In other cases, and this is also, I think, a learning that I'm excited about, by sending out the bat signal that it is possible to do an FRO, you get people to spend more time thinking about the FRO-shaped ideas in the first place. And so it's eliciting new concepts. And then sometimes we have to just go out and really directly say, we want you to take the time to write this white paper because we know you can, or something like that. Or we want this group to come together and do a workshop to generate that thinking. But just sending out the bat signal also elicits things that might not have just been sitting on the shelf. Yeah.
I think that is actually a really great point. Just from, it's almost, there used to be a question often after our technical workshops of, okay, if this would be a company, or could any of this become a company? Could any of this become a nonprofit? And now the question is, could any of this become an FRO? Like, the question has just changed. And there's obviously other organizational structures that are worthwhile doing, but people are really taking that concept by heart and are going out into the field with it, and are trying to not only pattern match different projects into that, because I guess that's not totally what you're looking for, but it's also really encouraging people to think a little bit more ambitiously. Like, before that, they only had a few organizational structures in mind, even when they were considering what they could be doing. And I think, especially now that there are a few living, breathing FROs out there, and it's not just a concept anymore, people are really shifting their thinking quite dramatically.
And I think it's great if that can back propagate, because I think there's a sort of more general question about scientific road mapping. How do you actually figure out what is the set of steps? What are the tools? What is the infrastructure, experiments that would need to be done along a certain path? And sometimes that's just happening. But in many fields, particularly where there's the perception that is farther out, it's hard to generate that road mapping. And so somehow I think that having this concrete, what would the FRO be, can, even if it's not literally going to do a FRO, it can just say, okay, let's just concretely have in mind, spend the thought cycles to think through this. People are so busy, right? Basically, people use up, in some sense, all of their free energy competing along some other dimension, right? Getting that next grant proposal, or pitching those VCs, or getting that experiment to work in the lab, that unless there's some kind of incentive for them or anchoring for them to do the thought cycles for something that has a different shape of output, it can be hard for them to do it. So I like that the FRO shape contributes to that. That's not at all to say that's the only shape. So I like what SpecTech is doing with their Brains Accelerator, where they've encouraged, if it's just a startup, maybe you'll find out it's just a startup, and that's fine, but there's other people that can do that. If it's an academic project, maybe that's something other people can do. But it could be an FRO, it could be a pitch for a program that the relevant person could go and run in an ARPA agency. ARPA program is a different type of coordinated research program, or it could be none of the above or something like that. It needs its own category. And FRO proposal, ARPA program pitch, and none of the above are things that can be good outputs. Yeah.
Yeah, and I should say that I think the applications for the next Brains cohort are open now for those of you that are interested in applying. But if you think about, for example, SpecTech as one other option to go to for people that are just trying to think a little bit more ambitiously about what they could be doing with their career, and in terms of like problems that they want to tackle, there's also, like, in the past few years, other organizations that have come online. For example, like ARIA, that we already briefly touched on, Future House, there's the ARC Institute here, there's Astera, there's Arcadia, there's like various other orgs that are at least trying to solve pretty ambitious science and technology problems, either by funding them, by having fellowships in them, and so forth. So if you look at this broader ecosystem, how did you see that evolve in the past few years? And are there any collaborations between the various different organizations that are trying to just raise the bar in terms of what's possible with scientific problem solving?
Yeah, and there's also even other categories, just if you want billionaire-backed startup or highly speculative FRO-like project that is structured as a startup.
Sure, yeah.
And I think that's also very valid, and there's some very exciting examples of that, like Cradle working on large volume vitrification. So these are all, it's not entirely clear what the cause and effect is. Some of it is frustration due to COVID. Some of it is financial dynamics in different fields like crypto in terms of funders, people encouraging each other to do these types of projects. So we are trying to nucleate as much collaboration as possible. So I think it's great if a sort of FRO creation studio, if you will, like us, could act in a way that helps an ARPA agency, let's say, to create the performers that it needs. So this is actually part of the motivation for the FRO model, is actually even in neuroscience and connectomics. Some academic groups did have ARPA funding. In this case, it was from IARPA, the intelligence ARPA, to do connectomics research. But the challenges of having a sort of distributed multi-lab collaboration, the ARPA toolkit was mostly being able to write checks to these individual distributed actors. What if we could get them all under one roof, and even more focused than what the ARPA incentivization of a collaboration does? And ARPA agencies also historically in different fields, they rely a lot on more like project creation or sort of contracting entities. So Eric Gilliam has written some good stuff about this too, about the old ARPA working with BBN and other organizations to actually do the engineering that was needed within the different ARPA programs. And so can we and can other organizations be a kind of create the performer mechanism for ARPA agencies? I think that's one interesting question. In what cases does that? Do ARPA PMs actually run against the situation where they don't have anyone to write the check to do the thing that they would otherwise want to do? You can have very general purpose engineering firms. I think if you want to make a new kind of fighter jet, you have Lockheed Martin and Raytheon and different types of contractors that the government can rely on. But if you are an ARPA PM that's interested in digitizing brains or something, it's okay, who's your contractor? And so maybe we could create a FRO for that. We're also trying to back propagate this more into the early stage thinking with the SpecTech Brains program. And we're trying to create a routing network of some kind. So if someone comes to us and maybe we don't have anyone who would fund that as an FRO, but maybe we think somebody would fund that as a billionaire-backed startup, or maybe they should go apply to be an ARPA HPM. To the degree that these organizations interact, everybody who shows up in one place can end up somewhere good at the end. So we definitely want to encourage that.
That is almost a job title in itself, someone who's just making sure that the inter-org paths are unblocked.
And you all are having a role in that too, which is definitely appreciated. So
yeah, it's a small one for sure. But I think one bit that I also really want to know is, if you think ahead, because you already mentioned a little bit in terms of numbers of FROs that are possibly out there, how many FROs do you think you guys can churn out in the next 5 years?
We've been going at a rate of a few a year. I think, as I was saying, I think that there's maybe on the order of 100 or so in a given kind of snapshot of science. Obviously, in 10 years, the world will have changed a lot and so on. But if you imagine a sort of over a roughly decade period, it would be great for the world to do on the order of 100, I think. I'm not sure exactly how that compares to how many ARPA programs does a given DARPA office do or something like that, but it's not totally out of the realm. If you also just add this up numerically, it's like a few $1 billion, which is a lot, but it's also, there are individual people who could just do that in a more discretionary way. And compared to the government science budget, it's actually not that huge. Yeah, so maybe you want the world to be able to be launching more on the order of 10 a year, whereas right now we've been doing 2 or 3.
Cool. I'm hoping that a bunch of other funders get inspired by this and join the efforts.
Yeah, me too.
Maybe my last question on my end, given that we have such a long-standing history in nanotech, and that's also how, like, the topic over which we first met, what do you think that field in particular needs to progress faster? Are there any projects in the nanotechnology realm, in the broader one, that you're excited about? I think you really champion this concept of a molecular 3D printer, but yeah, is there anything that you're excited about in terms of nanotechnology progress that could be soon on the horizon, or is already emerging, that you want to point out?
Yeah, I think it still needs a bit of an exploratory approach. The broadest answer, I think, is that it needs and has needed for a few decades more ARPA style coordinated research program type approaches. And there can be several of those within a given broader field. But I think the ARPA mechanism can work really well in the early stages of something because it also pulls the thinking of the researchers. With an FRO, they can interact a lot with it and collaborate with the outside community, and drive a lot of change, but it's often more about buckling down and solving a pretty well-defined set of technical problems as a single team in the same way that a startup would if it was trying to solve a deep tech challenge for a large VC-backed commercial type market. With nanotechnology, I think there's 4 or 5 different sort of ARPA-like programs that might be the best path. And I think that there is a challenge, which is that people are often asking for, okay, what's the commercial application that comes out at the end of those 4 or 5 years of work? And I think in nanotechnology, it's hard. And basically, with a general purpose fabrication method that's just bootstrapping to show its generality, for most of the things that we want in the world, we have come up with special purpose fabrication methods for them, which are not as general and maybe ultimately aren't going to have these self-reinforcing properties where they can become more and more general and more cheap and so on, that in principle nanotechnology would have. But we have special purpose ways of making those things. So that includes most of the things that go into the nanosystems we want to be exploring with. So we might be using cells or cell-free systems to manufacture the proteins that go into protein engineering. So we're far from this kind of exponential manufacturing takeoff, I think, still. And in a particular area, I spent a little bit of time during my PhD trying to think about biotemplated microchips, which is it's not the same problem as the positional chemistry problem. I think of positional chemistry, I often think about it in terms of DNA. Basically, you have some DNA double helix. It's about 0.3 nanometers per letter. So if you have some sequence of A, T, C's, G's between the one letter and the next, it's about 0.3 nanometers. It's about 2 nanometers along the sort of the diameter of that helix. And that's just a little bit bigger than the kind of covalent bond specification resolution that you need for sort of positional chemistry. That's a little bit bigger than that angstrom scale. Protein active sites and control of reactions in an enzyme active site is one step smaller than that. And then it's a bit smaller than relevant feature size of features on microchips. And so I was thinking a lot in terms of DNA nanotechnology, but I think that's the level at which we have a lot of programmable control right now through things like DNA origami. And we're starting to have some control with protein engineering that's a little bit smaller than that. Scanning probe microscopes can go smaller than that in terms of precision. But anyway, so we were thinking about how would we start with that DNA level of precision, single digit nanometer, programmable over some small number of nanometers as a kind of canvas with DNA origami, and how would you scale it up to full size microchip control? Could you position different nanoparticles or other discrete components at different parts of the chip? I think there's actually been a ton of progress in that direction of doing something like that. So implosion fabrication it's the opposite of expansion microscopy. It means you pattern materials into a hydrogel and then you shrink it. But it can shrink by a factor of more than 10 along each axis. And if you shrink something besides the wavelength of light down, you also get down to these single digit nanometer features. So we're getting more and more able to make these kind of biotemplated microchips. But that by no means that we suddenly displace Intel or TSMC, right, for chips, because that's been so optimized for the manufacturing problem that it's solving. So even though we have actually these breakthroughs like DNA origami or implosion fabrication, it doesn't mean that we suddenly replace Intel. It also doesn't mean that vaccines or other biologic drugs that are created in this way are going to replace more traditional vaccines or things like that. And basically, you need ARPA programs where you are allowing that the output of that ARPA program is another ARPA program, basically helping you spec. So you need a few iterations of a few parallel ARPA programs. And I think you actually make enormous progress on 3D printing, positional chemistry, more Lego digital protein assembly, chip scale, biotemplated chips. It's just everybody has a more near-term problem that they're worried about that is distracting them from working on nanotechnology at the level that they should. Yeah.
Yeah, as it's often the case with the general purpose technology that would unlock many other fields. Yeah. Thanks. That was a really, I think, neat summary of the field. And if anyone in the ARPA realm was listening to this, you guys know what create a waterfall of ARPAs for this particular topic.
Yeah, and that only adds up to a large but not totally unreasonable amount of money. So
great, totally unreasonable, not totally unreasonable, but take that. And that's my part of the podcast. I hand it over to Beatrice to dig in a little bit more into the existential hope part.
Yeah, I have a bit more. We call the Existential Hope program our North Star. So it's like the question of why are we working to develop all of these technologies? And so that's why I'm very curious to hear your thoughts on. So I'll just start with asking, would you say that positive or like optimistic about the future? And if you are, have you always been like, what made you so? Was there any particular event that like shifted your perspective on this?
I think I've down back to the sort of deep prehistory of reading things as a teenager. I think I'm probably most aligned with what Vitalik Buterin put out, so the DAC kind of framework. Not to say that there aren't huge problems and risks, but that the sort of toolkit of technology is actually so powerful that there is really a notion of creating defensive systems. And so I really like the idea of defensive systems. It doesn't mean it automatically works out this way. I think there are things that can be offense biased rather than defense bias. But if we can recognize that and create systems at the right scales, yeah, you can take the immune system as an inspiration. It doesn't always work, but it's a very powerful system. And so where are there analogs of we need to build something like an immune system? And that, fortunately, I think is something where, if in some sense the concern is that we get too good at making technology, then we should also be very good at making these immune systems. If we're really taking that seriously, we should also be able to make very powerful immune systems. So that's I'm a sort of DAC. That's the lever that I see, at least given my background. Yeah.
Yeah, DAC being like defensive accelerationism, which is, love the concept also. It's really gotten some traction, that meme lately. And like from, I guess, a more like social aspect or seeing a more like deep tech future, are there any, like, if we move away from the technology, are there any values that you think are really important for us to uphold as we continue to develop these technologies? I guess the DAC partly answers that, but is there anything else that you think we should keep in mind?
I guess I'm also inspired by some like notion of pluralism, that we need to be able to experiment and have different forms of society. And if anyone, even in service of DAC, you want to avoid this sort of hegemonic tamping down of change or tamping down of experimentation. It's something I think about sometimes from a neuroscience perspective. Yeah, human values, right? If human values, part of that is basically encoded by some brainstem and hypothalamus training signals or what have you, that is shaping our development in the context of a very particular set of social interaction affordances and stuff that we have. And I don't think we want to just fix those brainstem patterns. I would like to have more programmable control ultimately over my own mental states and values. But what's the danger in that? Because you have to maintain some sort of pluralistic system. Yeah.
Yeah. One question that we always ask is like this question of a eucatastrophe, which is the opposite of a catastrophe, an event that once it happens, the world is much better off. I'd be really curious to hear if you have any ideas for a particular event like this that you think, if we get this, would be much better off.
I do think, although it's I have ones at a couple different levels. So I do really think that right now people think a lot about AI, AGI. Some people think about this idea of can we like digitize or upload the brain. I think that is a little bit, maybe because it's a bit harder to define what success looks like, of just what if we could have a basic architectural understanding of our own brains? What if neuroscience actually succeeded as a science and we could have a basic architectural understanding of our brains in the same way we have a basic architectural understanding of DNA and RNA and central dogma of biology and how cells work? Like the things I was just saying about, okay, actually human values are programmed as a certain learning patterns and learning rules that are shaped by these brainstem or hypothalamus circuits. A lot of like human well-being is basically in there, what we want and how we interact, what we're motivated to do. So even just understanding those sort of, Steve Behrens calls this steering subsystem of the brain, even without every detail, I don't necessarily being able to completely simulate that, but just understanding the basic principles of how that works. What if neuroscience actually succeeded in some sense? We knew how this thing basically programs brains to go and learn. And that would be a big deal in many ways that we couldn't really predict. I think Steve Behrens is interested in that for an AI safety angle. That would be an example where a large learning system has been aligned with human values, basically, is through the steering subsystem of the brain. But also just all the things we could do for human consciousness, all the things we could do for human experience, if we actually just, there's some combination of sort of neuroscience and neurotech just didn't completely fail, right? It doesn't that you have to completely digitally upload your brain immediately into the cloud or something, or make a super brain. But even if we just knew what these sort of different subsystems of the brain were doing so that we could modulate them and understand the basic principles of how they work. So just neuroscience, like having a certain level of progress, similar to other sciences have, I think could be just enormous, but also very unpredictable what happens after that, because what do we choose to do with that? So that's at one level. Maybe at the meta level, it's what if we can remove all these operational bottlenecks to science, right? These sort of sociological operational bottlenecks. Yeah, again, it's not a law of nature that people struggle to create focused research organizations or ARPA programs or whatever, or don't have funding for creative ideas or something. That seems very solvable. So what if we could get science into a state where it was just limited more by really actually hard intellectual problems, which would still exist, versus by not being able to organize ourselves to prioritize doing science. Yeah.
So let's imagine we've achieved this, to be bold, both of your wishes. If you think of a world where that has actually happened, what do you think the main differences between our world today and that world is?
It's very hard to predict in both cases, because mine are not just concrete things. They're really, if we could really change science, things that would really change our understanding in a different way. So our understanding of what are possible goals. And I think there would just be so many ramifications. It becomes hard to predict. And one of the things I really want to make sure is that we actually get there. I think it would be great if we're like flying around on spaceships and stuff, but if we don't get to this kind of higher level of understanding, I really like certain sci-fi. Sometimes I find sci-fi gets it really right. Like in Steven Spielberg's AI movie, right? The aliens end up being very enlightened, right? And they understand a lot about psychology and values and stuff in the far future. And so I want to make sure we get to a point where we're not just the same us, but just flying around on faster spaceships. Although I think it's also important to greatly reduce, scarcity and increase optionality of what people do and increase economic growth. But I think people sometimes forget that science is going to look totally different and philosophy is going to look totally different in 100 years. Yeah.
Yeah, it's a bit like the technological maturity concept. Yeah, it would
another type of maturity that this will all enable. Yeah.
Yeah. And feel free to decline this question, but because you're answering on a very general level, which is clever, but what do you think for yourself that if we had this, what would Adam want to do? What do you think that you would value in that future?
Yeah, just not being distracted by dumb stuff. Getting to see that future at all and not being distracted by really dumb things. Yeah.
Yeah, fair enough. That's the point. It's very easy to get distracted today by a lot of things, both from ourselves and everything around us. In terms of like this, if we think of back to the idea of being positive or being optimistic about the future, is that something that you think is important? I'm asking in particular because I'm thinking about the sort of the question of the public perception of adopting a lot of these technologies and such. And I'm wondering if it's something that, in general, my sense is that like the general public is not necessarily super aware of the possibilities of a lot of these technologies. And a lot of like scientists can be a bit more on the gloomy side in my experience, but you have a very like action oriented. You seem to really think that a lot of these things are like very possible, and you're obviously doing a lot about it and making a lot happen. Yeah. What do you think we need to do? Do you think that we need to get the public on board more? Is there anything about this, like the public perception of this, that we need to change? Is it important to have a more like optimistic outlook on the future?
No, I agree. Yeah. At all these different levels. Yeah, no, I think of it as it's just hard to envision what good outcomes would actually look like. There's not enough work on envisioning good outcomes in detail, right? You can say, oh, this could be a problem, or this could be a problem, or this could be a problem. But there's not a lot of work on actually envisioning sort of the shape of good outcomes, even the very general shape. and even things that people think of as good outcomes in some cases. Oh, we avoid existential risk, but we're still having a huge international conflict around this or something. Yeah, more work on envisioning good outcomes and just with as much specificity as possible, because I think that people tend to dismiss that type of thinking as, oh, that would be nice, unless you provide enormous specificity. There's a double standard. I can just say, oh, this could go wrong. And even if I don't give a lot of specificity, people, oh, yeah, that could go wrong. But unless I say, oh, in incredible detail how this could go, people will still say, oh, that's just wishful thinking or something, or won't work out. So just envisioning positive scenarios in extremely great detail. And I actually include that at all these different levels, including if you're a researcher and you could have any tool in your field that you needed, right? What specifically would that tool be? That's a FRO question. So we're doing that within research of just what would it be? And then it turns out, okay, actually, yes, that costs millions of dollars, but it's not like it is like a time machine that is totally impossible, right? It's actually something that you could do. So I've been, inspired also by Tom Khalil, who's our board chair, and his sort of magic laptop thought experiment. Or if you could have 15 minutes with the president, but you could only ask them to do very specific things, call this person and have them call this other person and say this very specific thing. You couldn't just ask them to create magic for you, but you had to say, you call the CEO of this and call the president of that. And what exactly do you ask them to do? And if they would do all those things, then do you know exactly what you would ask them to do? This equivalent of that at a much smaller scale for science. And we somehow need this in the big picture too in society. And I think you're doing some great work on that, and we need a lot more work on that.
Yeah. I love I very much agree on the sort of double standards of this, and like negative versus positive futures, that if you say something can go wrong, it's very much agreed on. And in terms of the world building, I guess we're doing a lot of world building stuff right now to try to do that. But the FRO idea, I guess, is nice because it breaks it down even more. And we're trying to do that with world building, that we're trying to create this year in the future with this level of AI. Even being even more specific is probably good. But other than that, I agree very much in that keeping it open-ended is probably like the most smart thing we can do, because we don't necessarily know what's best for the future and such. But to inspire action today, it's probably better to have these like concrete things.
Yeah, even approximately correct, but concrete enough things can be really helpful. I find them to be really helpful. So,
yeah. We're down to the last 2 minutes, so I'll ask you, I think, 1 or 2 quick questions before we round off. But first, I would just love to hear, do you have any favorite resources that you would recommend? It could be a paper or a movie or a fiction or nonfiction, anything that you think has had a profound impact on you that you would recommend others to read.
I have a list of some of these on my website, on the talks writings page of my website. I just have this seemingly random list of all these different papers that I've really liked and stuff. And I'm not sure how helpful that is, but sometimes just the title of something will cause you to go down a rabbit hole that you might not otherwise go down.
That's perfect. We'll share the list and people can look at what's relevant to them. The last question I'll ask you is just if you could think of what's the best advice that you ever received.
I got some good advice about learning and trying to become a scientist from my undergrad research advisor. Said, don't neglect the time dimension in your own development. People are always asking you to produce things, and it's okay. Have I created my $1 billion startup yet by the time I'm 19 or whatever? It's actually, you're here to learn. So I would recommend people try to spend some time learning fundamentals. And if you need to spend 5 years learning physics or something, and you're worried that you're not going to be producing a lot of outside value for the world during those 5 years, probably just don't worry about it. It's not a very long time. At the end, you understand physics or something.
Yeah, that's probably very good advice. And yeah, you'll probably have the most impact in your like 40s or 50s or later in your
think on a long enough time scale that you're not neglecting your own development.
Yeah. That's great advice. Thank you so much, Adam, for joining. And
It's great to be here. Thank you so much.
Yeah, lovely to hear your thoughts and visions. And thank you for getting so much done, basically. So
thank you. Hope to see you both soon.